Hi, welcome to Chapter 9, Part 2. In this part of the lecture, we will talk about the conservation of momentum. Before we get going, just a quick review. In Part 1, we introduced the concept of momentum. And momentum, if you remember, is the product of the mass of an object times its velocity. So the law of conservation of momentum is one of the great conservation laws that our universe is described by. There are a few others that we'll learn as well. We'll learn about the law of conservation of energy a little bit later in this course. The law of conservation of momentum states that the total momentum of an isolated system is constant. And this is, by the way, what we mean by conservation of momentum. We mean that momentum is a conserved quantity, meaning it can't change. So that's basically the what we mean there. Interactions within the system, in other words, internal forces, do not change the system's total momentum. So if we have a system of three objects like this, and let's say they're bouncing around in here and bouncing off of each other and so forth, they are exerting forces on each other since they're interacting. But it turns out that because these forces are equal and opposite, they all end up canceling. And we're not going to prove or derive the law of conservation of momentum, but it's pretty simple to do using Newton's third law. And it's easy to show that the total momentum of this system does not change. Now, we said that the total momentum of an isolated system is constant. What do we mean by an isolated system? That's a collection of interacting objects that has no net external force on it. So some examples of isolated systems. First of all, weight and normal force you can think of those as external forces. However, they always cancel out if we're dealing with something on a horizontal surface. So in the case of, for example, billiard balls on a pool table bouncing off of each other, there is the external force of weight pulling them down, but the table's pushing them back up, so the weight and the normal force cancel. So all these billiard balls are really experiencing are the forces between each other as they collide with each other. And those are internal forces. And so therefore the total momentum of this system here does not change. And especially, if we exclude friction. Another example is two cars crashing. So again, the weight force and the normal force are going to balance out. So we can consider and model two cars crashing as an isolated system. So most of this, the remainder of this lecture, we're going to be just showing a bunch of different types of examples and applications where we can apply the law of conservation of momentum to solve problems. So in order to do some problem solving with the conservation of momentum law, let's see what how the law plays out in terms of equations. So what conservation of momentum tells us is that the change in the total momentum of the system is equal to 0. All right, this just says that the total momentum can't change. So we have delta P total. All right, now remember, P is momentum, which is a vector. So we have to add up all the momentum vectors of the system here, and if the change in those vectors will be 0. So that by itself is a little tricky to figure out how we can use that to solve problems. So let's take it a little further. So what do we mean by the change in the total momentum? Well, this is the final total momentum. So we have P total F for final minus P total I for initial. So this is what we mean by the change in total momentum. And again, this has to be equal to 0. So basically, we can take this term here, the initial momentum, and let's move it over on the right side. So what we're saying is that the total final momentum of the system is equal to the total initial momentum of the system. And furthermore, let's suppose our system consists of two objects. Most of the problems, in fact, all of the problems that we'll be dealing with in this course are just going to have two objects in there to keep things as simple as possible. So let's say we have object 1 and object 2, and they're somehow interacting. All right, and again, this will become more clear with examples. But what we mean here is that on the left side, remember, these are the final momentum. So we're going to take object number 1, its final momentum, we'll call that P1F, and we're going to add it to object 2's final momentum, P2F, and that has to equal to object 1's initial momentum here plus object 2's initial momentum here. So we're just, we're starting with this kind of compact statement up here, and we're just step by step, we're expanding it out into a form that we can use. And obviously, remember that momentum, P, is equal to mass times velocity. So that's usually what we're going to deal with, the masses and the velocities. Now, one thing we have to take care of here is that, these are vector quantities. So remember, when we want to add vectors, we can't just add numbers together. We have to deal with their directions as well. So typically with momentum problems, we're going to deal with components. And later on in this lecture, I'll show you how we do a two-dimensional conservation of momentum problem. But what we're going to do is break up the vectors into x components and y components. So what this tells us here is that the x components of momentum are conserved. So we have P1x final plus P2x final equals P1x initial plus P2x initial. And so these are just the x components of these vectors here. And then likewise, this equation down here tells us that the y components of momentum are also conserved. In other words, the final y components of momentum, if we add them together, they must equal the initial y components of momentum added together. So a lot of equations on this slide, I realize that, but this will become more clear hopefully after we work through a few examples. So the first several examples that we're going to do are all one-dimensional problems, which makes it as easy as possible. We're not going to have to deal with vectors or trigonometry or anything like that. So let's just go through some of these problems. So in this first example, we have Sandra here and David are on ice skates, and they face each other, and they push off from each other, as shown. So after the push, it's told that Sandra moves back at 2.2 meters per second. And the question is, how fast does David move back? All right. So we can kind of see that, by the way, their masses are given here. David's mass is 80 kilograms. Sandra's mass is 45. So when they push off on each other, we can sort of predict that they're going to fly apart from each other because they're both pushing against something. Interestingly, this type of problem is an example of what is called an explosion in physics. And that is, we have particles of a system are moving apart due to internal forces. Okay, so in a bomb, obviously, all the shrapnel in the bomb flies apart due to the forces caused by a chemical reaction. This is a little different, obviously. There's no explosion, explosive chemicals or anything, but the two actors here are pushing against each other. And so that is an internal force, and this constitutes a simple example of what's called an explosion. So anyway, let's go ahead and analyze this problem. We want to figure out how fast is David going here. So we're going to apply the law of conservation of momentum. And obviously, we only are working in the x direction. So we're going to use the equation here for the x direction. So we have the, we'll call object number 1 is going to be David. All right, so this is P1x final plus P2x final equals, and then this is Sandra over here. Oh, I'm sorry, this is David here. P1x final is David, P2x final is Sandra. And then over here are the initial momentums of David, he's object 1, and Sandra, object 2. So what I'm going to do now is replace P with the definition, remember, of momentum is mass times velocity. All right, so I put subscripts in here to try to keep track of David and Sandra. So D for David, S for Sandra, and F for final, and I for initial. All right, So one thing that makes this problem a little bit simpler to work with is that if we look over here on the right side, notice these are the initial momentums of David and Sandra. So this is the initial picture, and this is the final picture after they push. So in the initial picture, of course, they're not moving yet. So we can set both of these terms over here on the right side to 0. So now all we have to work with are these two terms here, the final momentum of David and Sandra here. So let's set these two, let's equate them, all right, by moving this term to the other side. Just do some algebra here. And so we have David's mass times David's velocity is equal to negative Sandra's mass times Sandra's velocity. And we are solving for V sub d, all right, David's final velocity. So all we have to do is divide by the mass of David on both sides of the equation. And so here is our expression for our answer, and now we just have to fill in numbers. Sandra's mass is 45 kilograms. Sandra's final velocity was given at as 2.2 meters per second, and David's mass is given as 80 kilograms. So, and then remember there's this minus sign here that we picked up right here. So on our calculator, this turns out to be negative 1.2 meters per second. Now, a couple things, a couple comments here on this answer. First of all, there is a minus sign in front of David's velocity. Now, why is that? What does that tell us? You're right. David is moving to the left. Okay, Sandra's velocity was positive 2.2. David's velocity is negative 1.2. That's because he's moving to the left, as we guessed. All right, the other thing is, why is David moving more slowly? He's only going 1.2 meters per second compared to Sandra, who's going 2.2 meters per second. Why is that? Well, the reason is David has more mass. So remember that the initial system here has no momentum. That means the final system has no total momentum. So David's momentum, which is negative, has to exactly balance out and cancel out Sandra's positive momentum. So since David has more mass, he has to move slower to have the same momentum as Sandra, who is less massive and moves faster. In the next video, I'll show you a simulation tool that we can use using carts, and we can simulate this type of explosion example. So let's go and look at the video now. This is a collision simulator on a website called physicsclassroom.com. What this does is it allows you to change the mass or position or initial velocities of these two carts here, and you can choose whether you want to do an elastic collision, an inelastic collision, or what we're going to do here in this demo is what's called an explosion. And remember, like in the problem we just saw with the two ice skaters, an explosion is when you have two or more objects initially together, and then they move apart because of some force. So what we're going to do first is set up both of these carts to the same mass. So notice down here you can select different masses. So I've selected both of them to be the heavy 3 kilograms. Let's go ahead and run this and watch the simulation. So you can see they both move apart after the explosion with the same velocity. Now let's reset it, and let's make the red cart heavy here at 3 kilograms, and the blue cart is lighter at only 1 kilogram. So this is like our two figure skaters, the two skaters on ice. This is the heavier man here and the lighter woman. So let's see what happens now when we run the collision, or the explosion, I should say. So now you can see that the lighter cart moved much faster than the, we'll do it one more time here, than the red cart. And again, remember that the total momentum here is 0 before and after. So even if I go back to our initial condition where both of them have 3 kilograms. Right now, the momentum is 0, obviously, because they're not moving. But after the explosion, the momentum is still 0 because this one has negative momentum and the other one has positive. The last thing I can do here real quickly is just reverse the masses. And now let's have the blue cart be 3 kilograms heavy, and the red cart is the light one. So what do you predict will happen? Which one will move fastest now? Well, let's go ahead and run it. So now you can see that the red cart moves faster, and again, it has to in order to conserve momentum. The total momentum of this system has to be 0. So since this cart had less mass, it has to move faster and in the opposite direction as the blue cart. So here's another example in one dimension, and this is a little bit different. We've got a 120 kilogram linebacker. He's the New York Giants player here, is running at 5 meters per second, and he sacks the quarterback, and the quarterback's mass is 90 kilograms, who is initially standing still. How fast do they move together during the tackle? All right, so this is obviously a different type of problem. What happens here is, you have the one object, the linebacker, flying in and hitting the quarterback who is standing still, but then they become stuck together. All right, notice they're basically one object. They behave like a single object after the collision. So this is an example of what is called a perfectly inelastic collision. It's inelastic because they don't bounce apart. They stick together. All right, you can think of it like two lumps of clay that are thrown together and they just stick together as a single blob. So let's see how to tackle this problem, no pun intended. Here's our statement again of conservation of momentum in the x direction. So what happens here on the left, notice we have our final momentum of the linebacker and the quarterback here, all right? Now, since in the final position, that's right here, they are stuck together as one object. So we're going to use the total mass of both the mass of the linebacker, that's the LB, and the mass of the quarterback, MQB. We're going to add their two masses together as the total mass of this one object after the collision. And obviously, since they're stuck together, they also have to move together. So they have a single velocity, which we'll call V total, final. Okay, so that's on the left side. Now on the right side are the initial momentums of the linebacker here and the quarterback here. So let's take a look at those. Well, the linebacker has mass LB, mass M sub LB, and he has an initial velocity, which we were given that up here. Now, what about the quarterback? Well, the quarterback's initial momentum is 0 because remember he was standing still before he got tackled. So this term here we don't have to worry about, and we can just put in a 0 there, which is kind of nice because that term drops out. So our goal here is to solve for how fast do they move together during this tackle here. So we're going to solve for V total final, and all we have to do is divide everything by this, the total mass of the whole system. So here's our answer. It's mass of the linebacker times initial velocity of the linebacker divided by the total mass of the linebacker and the quarterback. So plugging in our numbers, we have 120 for linebacker's mass. His velocity was 5 meters per second. And these are the two masses added together, the linebacker here, quarterback here. And so this comes out to be 2.9 meters per second. So notice that the linebacker was running at 5 meters per second. But after the collision, right, after he sticks together with the quarterback, his velocity has now slowed down to 2.9. Well, this is because momentum has to be conserved. All of a sudden, our object is more massive, right? Now we've got two objects stuck together. So in order to conserve momentum, the velocity had to slow down. We can also demonstrate this using the collision cart simulator, which we'll look at next. We can simulate the problem that we just looked at with the linebacker tackling the quarterback using the collision cart. So I've set up the red cart over here with an initial velocity of 5 meters per second. And notice I've added some, weights to or mass to this cart. So this represents the heavier linebacker. The quarterback is going to be the blue cart here, and he's going to be at rest at 0 meters per second, and also a lighter mass. So let's go ahead and, and then down here, of course, I selected Inelastic Collision, meaning that the two carts are going to stick together. So let's go ahead and run the simulation. So here comes the linebacker, hits the quarterback, and now notice after they collide, the speed is reduced. So it's 5 meters per second there. After the collision, they're both traveling at 3.8 meters per second together because they've basically become a single object. Now, one thing we can do here is we can see what happens if this player that does the tackling is going to try to tackle a heavier player. So let's add some more mass to the quarterback, and we'll take away some mass from the linebacker, and let's watch it now. So now you can see after the tackle, they still move together at the same speed, but notice how slowly they're going now. That's because the initial momentum here, which is given from the linebacker here, is less because his mass is smaller now. So therefore, the total mass afterward is less as well due to conservation of momentum. Here's a little different example from the previous two. We've got a crane drops a 2,000 kilogram boulder vertically onto a 4,000 kilogram truck that is initially moving at 4 meters per second. What is the truck's speed right after the rock lands? So here's a picture of our problem here. We've got this truck here moving along to the right at 4 meters per second. And this boulder here, this big rock, falls and drops directly on the back of the truck. And afterwards, the truck and the boulder together are moving forward, okay, with some velocity. And we're going to try to figure out what is this final velocity. So the way to approach this problem is to realize that this is really still a one-dimensional problem of momentum. Even though this rock is falling vertically, the rock has no initial x momentum in the horizontal direction. So we can ignore the y momentum of the rock since we are only interested in the x motion of the truck. So in doing that, we can say that the final momentum of the system is equal to the initial momentum of the system. And we're talking about in the x direction here only. So our final momentum is this. We look at this picture here, and we have the truck and the rock added together. There are two masses. That's the mass times their speed, all right? That's v sub final, which we're trying to solve for. The initial momentum of the system, we look at this picture here, but remember, we're only dealing with the x direction of momentum. In other words, we're only looking at the horizontal motion here. This vertical motion doesn't affect the horizontal motion at all because they're perpendicular to each other. So the initial momentum here, p sub I, is just the truck. It's due to the truck. It's the mass of the truck times its speed, 4 meters per second, okay? So we can solve for v final, which is right here. Again, we're going to have to divide everything by the total mass of the truck plus the rock. So our answer, v final, is mass of the truck times initial velocity of the truck divided by the total mass of the truck and the rock. So plugging in all our numbers, you can see them here. It comes out to be 2.7 meters per second. So what happens here, notice the truck was going at 4 meters per second. After the rock falls in it, the truck's only going 2.7 meters per second. Now, why is that? Well, it's because the truck's mass increased, all right, because that boulder added to it. So if the mass of the truck increased, then its velocity would have to decrease in order to preserve or conserve the amount of momentum that it had here. So this, I'm going to show you a video that I took at home, a demonstration of this same problem. We can demonstrate the conservation of momentum principle that we saw in that previous problem using a skateboard here rolling across the table. So what we'll do is as a skateboard rolls by, I will drop this 25-pound plate on top of the cart or the skateboard, and we'll watch it slow down as it conserves momentum. So here we go. Let's take a look at another inelastic collision example. We've got two cars with the masses and velocities shown below collide head-on and stick together. What is their final speed? All right, so we've got this head-on collision here between car 1 here has a mass of 1,600 kilograms. It's going 10 meters per second. Car 2 has a mass of 1,200 kilograms, and it's going faster at 20 meters per second. So when they crash, they stick together. All right, we're going to assume that they don't bounce off of each other. They just they lock together. So this is another inelastic collision example. And we want to know what happens when they stick together like this. Do they move at all? Do they move to the right? Do they move to the left? So to solve this, again, we're going to apply the law of conservation of momentum. All right, and we're dealing only in the one direction here. So on the left side, remember, these are the final momentums again. So if we look, and this is the final picture here, the after collision picture. And we've got basically one object because they're stuck together. So we have the total mass of the wreckage times V final of the wreckage. And that's equal to the initial momentums of each of these two cars individually. So M1 V1I times plus M2 V2I. Okay, so the total mass, of course, is M1 plus M2. And what we're trying to solve for, again, is the final velocity, this final velocity here of the wreckage. So as we've done in the last couple of problems, we're going to be dividing everything by the total mass here, M1 plus M2. We're going to divide everything over here on the right side. So we end up with our answer, V final is equal to M1 V1 initial plus M2 V2 initial divided by the total mass. So we can plug in our numbers. We know all these numbers. We know M1 is 1,600 kilograms. Its M1 speed is positive 10. And then for M2, we have 1,200 kilograms. And remember, car number 2's velocity is negative 20, right? It's 20 meters per second, but pointing to the left. So that's where this minus sign comes from. Okay, we have to remember that minus sign. That's important. And then we divide by the total mass of the two cars, 1,600 plus 1,200. So we end up with negative 2.9 meters per second. That tells us that the total, the wreckage here stuck together is going to be moving to the left. That's why there's the minus sign tells us that we're moving to the left. By the way, the reason it moves to the left is apparently this car, the lighter car, ended up with more, it has more momentum than this one does. Okay, so this leftward momentum dominated over the rightward momentum. So the wreckage moves to the left. So again, we can look at some collisions here in a video, in a collision video that you'll see next. Let's go ahead and analyze the head-on collision of the cars using our collision simulator here. So we're going to look at a couple different scenarios here. The first scenario, let's assume that both cars here, the red and the blue, both have the same mass. All right, I set the mass as equal down here to 3 kilograms. And they also have the same speeds. Of course, the red car is moving to the right at 10 meters per second. And the blue car is moving to the left at 10 meters per second. So let's go ahead and run the simulation and see what happens. So you can see after the collision, the wreckage here is not moving at all. And this is because the initial momentum of this system is 0. Now, how can that be? Well, the red car has momentum moving to the right, so that's positive momentum. The blue car has momentum moving to the left, which is negative momentum, and they exactly cancel each other because the cars have the same mass and the same speeds. So after they collide, the wreckage here has to also have zero total momentum in order for momentum to be conserved. And so that's why nothing moves after the collision. Now we can try to do something similar to the problem. We can set the red car was moving slower, the one on the left. We'll change that to 5 meters per second. And it was more massive, so we're going to keep that at 3 kilograms. The blue one was moving faster, so we'll keep that at negative 10 meters per second. But it had less mass, so I'm going to change this to 2 kilograms here. So let's see what happens now after they collide. So you can see after the collision, the wreckage is moving to the left. What that tells us is that the blue car had slightly more momentum than the red car. Now, even though the blue car is lighter than the red car, remember it was going faster, and so that was enough to give it more momentum. So as a result, everything moves to the left. Let's change the parameters a little bit. Let's take our red car and change its speed to 10 meters per second, and we will slow down the blue car to minus 5 meters per second, and let's see what happens now when they collide. So now you can see the wreckage after the collision moves to the right, and the reason for this is because now the red car had more momentum than the blue car. So the total momentum of the system was positive in this case, and it has to be before the collision and after the collision as well. All right, well, I saved the best for last. So the last problem we're going to do is a two-dimensional example. And when we work with two-dimensional collisions, it's always a bit more involved and tedious because we have to deal with components and we have to solve for each of the components. So it's sort of like two problems instead of one problem. So let's look at the situation here. We have a hawk attacks a pigeon in midair by diving down at 18 meters per second at a 45-degree angle. So here you can see the situation. Here's our hawk diving down. You can see that the angle here of descent is 45 degrees. And here comes our poor pigeon flying along horizontally like this. And the hawk is, being the hunter he is, he times this perfectly and he's going to grab the pigeon at this point right here. And afterward, their conservation momentum will dictate in what direction and what speed the hawk and the pigeon end up flying at right after the collision. So we're given the velocities. The hawk is diving down at 18 meters per second. The hawk's mass is 0.8 kilograms. The pigeon flies horizontally at 9 meters per second, so that's VP here, and has a mass of 0.36 kilograms. Determine the speed and direction of the hawk after catching the pigeon. So our goal here is to find this vector here, the final velocity vector, find out its magnitude, which is the speed, how fast they're going, and figure out what this angle theta is, which tells us what angle they move at. So the way to attack this problem with two-dimensional problems is to basically work with the components. We're going to sort of solve two different problems here. We're going to do one for X momentum, the horizontal momentum, and we're going to solve another problem for the Y component of momentum. And then we're going to put these results together using some trig to figure out our final answer. So let's see how we do this. So let's just worry about the X momentum itself. All right, so the hawk remember the hawk was moving down at a 45-degree angle. So we're going to replace that vector with its components. Its Y component vector pointing down and its horizontal or X component pointing across. So this is VHX, this vector here. This is VHY, and VH is for the velocity of the hawk. So in the X direction, the final X component of momentum is, again, this is an inelastic collision. Remember, the hawk and the pigeon are stuck together at the end. So we have the total mass of the system here, the two masses added together, and this is the X component of the final velocity. all right? The final velocity, you can see it down here in this picture, is this red arrow, but it has, since it's a vector, we can think of its x component as pointing to the right like this, and its y component pointing down. So we are going to find this x component right here. That's v final x, okay? And on the right side, we have the x component of the Hawk's initial momentum. Now that's equal to the mass of the Hawk times the velocity of the Hawk times the cosine of 45, right? This is a right triangle here, and this side down here is equal to the hypotenuse, which is VH, times the cosine of 45. So that's where we get those from. Now the pigeon, remember, was flying horizontally. So the pigeon, we don't have to do any trig for the pigeon. The pigeon's x momentum is just equal to the mass of the pigeon times the pigeon's velocity. So we can now solve for the final velocity x component, v sub fx. This term right here, just by dividing all of this stuff over here on the right, divided by the mass total. So here's our equation. And all of these quantities were given to us. The mass of the Hawk, the velocity of the Hawk, mass of the pigeon, velocity of the pigeon, and then the total mass is just the two masses of each bird added together. So all of this comes out to be 11.6 meters per second. Now remember, all we found here was this component right here. We found the x component of the final velocity is 11.6. Okay, that's in the horizontal direction. But obviously, this system is also moving in the vertical direction. So let's now turn to the y momentum, conservational momentum in the y direction. So again, we can write that the final momentum in the y direction is equal to the initial momentum of the Hawk and the pigeon in the y direction. So over here on the left, we have the total mass times the y component of the final velocity. So now we're looking at this component right here of the final velocity. And for the Hawk, on the right side, its y component in the initial velocity of the Hawk is this vector here, which is the hypotenuse, VH, times the sine of 45. Now we also have to be careful of the direction. Obviously the Hawk is flying down to attack the pigeon, so his velocity is negative. So that's why there's that negative sign out in front there. Now, what about the pigeon's vertical momentum? Well, the pigeon is moving horizontally. The pigeon's not moving vertically at all. So the pigeon doesn't have any vertical momentum or y momentum. So that term is just zero. This second term here is zero, so that's nice. Finally, let's solve for this v sub fy right here. We just divide everything by m total and plug in all our numbers, and we get negative 8.78 meters per second. This is the y component of the final velocity of the Hawk and the pigeon. We have just found this. So we now know what the x component is, 11.6, and we know what the y component is, negative 8.78, let's figure out the final speed. In other words, the speed of this velocity vector here is just the magnitude, and that is the hypotenuse of this right triangle. So we're basically using the Pythagorean theorem. We know the x and the y component, that's this side and this side, and the Pythagorean theorem says that the hypotenuse squared is equal to this side squared plus this side squared. So we can solve for the final velocity is the square root of the squares of each of those components. So in this equation here, v final x, we use this number, 11.6. Remember to square it. V final y, we use negative 8.78. We square that. We add these two numbers together, take the square root, and we get 14.5 meters per second. That's how fast the Hawk and the pigeon are going after the Hawk grabs onto the pigeon. The last part is, what is the direction? Well, to find out this angle here, theta, we can remember that the tangent of theta is equal to the opposite side over the adjacent side. So that's the y component divided by the x component of velocity. And so theta is equal to the inverse tangent of all that. And so we can plug in our vector, lengths of these vectors here. So VFY, that's this guy here. Remember, it was 8.78. We're just using the positive, physical length of that vector. And then down here is VFX, which we found up here to be 11.6. So we're finding the inverse tangent of 8.78 over 11.6. So calculate this first on your calculator, and then punch the inverse or arctangent button, and you'll get an angle of about 37 degrees. Here we're going to simulate the hawk and pigeon problem using a two-dimensional collision simulator here. So I've set this up so that this object number 2 up here is our hawk, and it has a higher mass than the pigeon, which is down here, which is the red object number 1. So I've also set their velocities so that the pigeon flies horizontally, like in our problem, and the hawk is going to dive down from above. So we can watch what happens during, before, during, and after the collision. So there they collide, and then you can see after the collision they move together as a single object, still moving in the downward direction, because remember the hawk's downward momentum carries the combination of the two objects together.